Welcome back to this lecture on thinking about linear stability, order parameters, pattern formation in general. And so I want to build on the themes that we talked about last time, which is this idea of pattern formation, which is when a system goes unstable, especially a spatial temporal system, what do we expect to happen in that scenario? Is there a way for us to quantify it, characterize the dynamics, and start to explore mathematical structures that allow us to really understand and pull apart the kind of things we would see at instability points or bifurcation points in spatial temporal systems. So again, I want to come back to something like this, a spatial temporal system of this form here, some nonlinear evolution equation. And now in this case here, unlike the last lecture, I'm going to go ahead and add some kind of small perturbation to this, some epsilon f. So I can have a perturbation to some nonlinear evolution equation. And what I'd really like to understand is the stability of this system, in particular solutions to this system, and what happens when they go unstable and the kind of behaviors that they would exhibit. Not only the kind of behaviors they exhibit, but how can I analytically characterize this in some kind of, in some kind of way. And this is going to really come down to us using our perturbation theory and also using our multiple scale analysis that we did previously for solving a variety of problems, including boundary value problems, but also generically any kind of system where we think about perturbative effects in the dynamics. So I want to expand about a given solution. What I'm going to assume here is that there's some base solution. Just call it U naught. And this is in the case epsilon is 0. So if I throw out that forcing term, that in fact I have a base solution, U naught, and it's a function of xt. And what I do here is put theta. So theta are all the parameters in the system. So when I write down this solution, it has some constants. I'm going to call those parametrizations of that solution. Remember, when we do multiple scale analysis, parameters are no longer constant. They often evolve on slow scales. That's exactly the way I'm going to think about this theta. I'm going to write down this base solution with some parameters, which is a parameter vector theta, and all those parameters can depend upon slow time scales. And then I would like to understand then how do those slow time scales evolve and modify that leading order solution. So what we're going to do is introduce multiple scales. But now it's a spatial temporal system. So when we considered perturbation theory before, we either considered spatial system or temporal system. Now we have both space and time. And so I introduced slow scales, tau, and slow spatial scales, xi. So here, there's a small parameter, epsilon 1, epsilon 2. Tau is slow time. Xi is in some sense slow space, or longer spatial scales. Both epsilon 1 and epsilon 2, the way you would determine what they should be, also in relationship to each other, is through doing dominant balance asymptotics. We talked about this previously, but typically this is something where you're going to look at what you would generically put in epsilon to be small, epsilon 1 and epsilon 2 to be small, and then you would figure out how space and time should balance in order for you to get some kind of solution that actually makes sense. If you don't have the balance right, you often lead to it leads to nonsensical results or trivial results. So what you would want to do is figure out how to balance those. We're not going to talk about that right now. We're just going to say there exists some slow space and slow time scales. And the big deal with that is that now the parameters theta that we talked about, which were specifically, they were considered constants before parametrizing our leading order solution, are now functions of slow space, slow time. Okay? So they're no longer really constant. They depend upon these other variables. Okay? All right, so if we're going to do multiple scale expansions, we have to rewrite our governing equations, not just in x and t, but in x, xi, t, tau. So now there's 4 variables. So think about what this means. So t, I can change this through chain rule to, it becomes d dt plus epsilon 1 d tau. X, change it to dx plus epsilon 2 dxi. And here, this is the second derivative. And notice that you pick up a cross term and then a second derivative c with an epsilon 2 squared in front of it. So the whole idea here of multiple scales is take your dependence not just from xt, but now everything depends upon x, t, xi, and tau. So there's now 4 scales. Xi and tau are your slow space, slow time. And the reason we've introduced them is because when we have this flexibility, we've already talked a lot about multiple scale expansions and how what they essentially allow us to do is allow us to make sure that when we do a perturbation expansion that the Fredholm alternative theorem is satisfied. And this is exactly what's going to happen in this case too. When we do a perturbation expansion, having those slow scales available to us, having the parameters evolve on a slow scale, are going to allow us to satisfy the solvability conditions, and they're going to impose constraints then on the evolution of those parameters, which are actually quite insightful. So that's what we're going after. There's one other small scale we're going to introduce, which is called, epsilon 3, which is going to tell me how close am I to the bifurcation parameter. So all of this analysis is going to be done around some region where the solution changes. In other words, where there's a bifurcation in this spatial temporal system. So epsilon 3 is going to measure how close mu is to mu of c, which is where the bifurcation occurs. And so that's going to be small as well. Okay, so I have 3 small scales, all that are going to be determined by dominant balance. And so what I'm going to do here is I'm going to take my solution now, which is a solution of x, t, xi, and tau. And now I already had a leading order solution, u naught, that was dependent upon theta, which was constant before. But now theta, I'm putting its explicit representation as a function of tau and xi, plus perturbation. So this now is my solution in this perturbative approach. And so we're going to talk about in the next 2 lectures is this idea of when things go unstable, how do I characterize them? And there's various ways to characterize them in which we can sort of start to capture the dynamics beyond the bifurcation. And so we're going to look at 2 different ways. One is just an ODE way in this lecture. In the next lecture, developing what are called envelope equations or order parameters that are the descriptions of what happens after the onset of instability. Okay? Once you walk through the bifurcation point, what's the dynamics that occurs near there and how can we get to it? And this is the kind of formal way to treat this, because this is going to allow us to ask that question and to answer that question. All right, so if we plug that in, what we find, so we have the leading order solution, and in the next order, the linearized evolution is given by here. We're not going to go any higher than the next correction, which is the order epsilon. So what you end up with here is u tilde t is equal to, there's a linear operator. This linear operator depends upon the leading order solution u naught, as well as its parameters theta, and of course mu, which is the bifurcation parameter, plus some right-hand side term, which also depends upon the leading order solution, and now also depends upon slow, and specifically the slow evolution of the leading order solution, u naught tau, u naught xi. And by the way, the slow evolution of the leading order solution comes through the parameters theta. Okay? So this is what we're going to get. So you do a formal expansion with slow space-time scales, you get something like this. And as before, the most important thing that has to happen once you get to this formulation is Fredholm alternative theorem has to be satisfied. So there is a solvability condition that you're going to have to enforce to get solutions that don't generate fictitious secular growth. So the solution form we're going to take here is exactly what we did in the last lecture on pattern forming systems. We're going to say this solution of the linearized equation has some amplitude. Before we said it was constant, but now it can depend upon slow time and space. E to the lambda t plus I k tau x. So now notice what I've done here. I've set my lambda and k to explicitly depend upon the slow time scale, tau. Okay? So they're not constants. I'm letting A eat up the slow spatial scale xi, but these here in my dispersion relationship, the lambda and k that are in part of my dispersion relationship, they're explicitly depending upon the slow scale tau. So what happens is when you push this in here and you come to this problem here, what you're going to get is if you actually say, okay, if this is my solution form, and if I impose that in fact this function f has to be orthogonal to the null space of the adjoint operator of L, right? This is the solvability conditions. What it's going to do for you, Fredholm alternative will actually impose, for instance, evolution dynamics on the amplitude there. A of tau is going to be some evolution. This evolution is basically enforcing that the Fredholm alternative theorem holds. Or more broadly, any of your parameters theta also are going to have some kind of slow evolution enforced. Here you go. It's just rewriting that theta tau, and then lambda tau here as well can be some evolution equation. I think actually this is supposed to be k of tau, not theta of tau. My mistake. So basically what you're doing is when you bring this in, by enforcing the Fredholm alternative, it enforces what the slow evolutions have to be in order for you to have that this thing here does not have any component that's generating secular growth terms. Okay? So it goes right back to where we started when we were doing regular perturbation theory and developing this idea of Poincaré-Lindstedt in multiple scales, with the entire goal of it to be to eliminate secular growth and satisfy solvability. That's all we're doing here too. It's just that now it's in a partial differential equation setting, so space-time, not just time or space. So I want to do a specific example because, in fact, that's sort of your, what I just showed you was sort of the abstraction of what you do generically. But let's go to a very specific problem. This is going to be in the nonlinear Schrodinger equation. Here it is. Given by here, it's IUT plus 1/2 UXX mod U squared U. So it's a nonlinear evolution equation. I is the complex number, square root -1. And so it's got some complex evolution. The field itself has real and imaginary parts. And I'm going to force it with some function f, epsilon f. So epsilon small. Now the leading order solution to this are what are called soliton solutions. There is a soliton solution to this for epsilon is 0, which is given by this hyperbolic secant and is parametrized by an amplitude eta, by an offset. This is essentially where the 0 point of this thing is, x naught, by some phase term, center frequency term xi, and some phase phi naught. Okay? So in other words, this problem is parametrized by 4 parameters, okay? Which normally you would think of them as constants. And by the way, dx naught dt is c, and d phi dt is 1/2 x c squared plus eta squared. So this is these hold for this. So these 4 parameters, normally we think of them as constant. But of course, in what we're going to do here, since we're going to perturb the system, we're going to say, well, what if those 4 parameters actually depended upon slow time? What would happen to this soliton solution, which is a localized wave, under perturbation? And by the way, this nonlinear Schrodinger equation comes up in optical fiber communications, where you can propagate pulses of light, these soliton themselves. These were first experimentally demonstrated in 1980 by Lynn Mollenauer at Bell Labs at that time. And they were considered a very promising technology for propagating optical waves down fibers that would encode information in bits of 1s and 0s. Okay? And so these, what you really want to understand is if these get perturbed, how do they get deformed? And so there was a big study back in the 80s and 90s about how stable are these solitons to perturbation. And so we're going to address that right now. So there you go. So we have this. Here's our leading order solution. And now, just like I said, here are the parameters, eta, xi, x naught, phi naught. And now what we're going to say is they can depend upon slow time tau. So then we're going to do our perturbation expansion. We're going to say uxt is equal to u naught e to the I phi, that's the phase of the field. And I'm just going to add this perturbation here. Notice I've factored out a common phase, and I did this before 2 lectures ago with, last lecture with nonlinear Schrodinger. So I'll just for convenience, I'll factor the phase out, and I really care about the evolution of u tilde in this setting. And remember, epsilon is small. When you linearize, here's your linearized evolution. There it is. Linearized evolution here, where the right-hand side forcing F is given by this object here. So this is kind of a long calculation, but there's a phase factor in front of it. There's the actual right-hand side term, F, and then notice what happens here. So this here is f hat. F is the original perturbation to the system, and all these terms that come and enter into the perturbation to the linearized equation are due to the slow evolution dynamics of the parameters. Notice C of tau. There's x naught tau, phi naught tau. So in other words, at the next order, the slow evolution of what we normally would have considered constant now are introduced into a right-hand side forcing term, f. This forcing term, this is what we're going to have to impose our solvability conditions on in order for us to get a solution that doesn't generate secular growth. Okay? So what we do with this here, this solution is complex field. So I'm going to write it as terms of real and imaginary parts. So U tilde is the real part plus an imaginary part. And so you decompose that into the real and imaginary parts. And now it becomes the evolution of the real and imaginary parts satisfy this linearized operator here. There's an a squared over 2. There's these two operators, L minus, L plus, which take on this form right here. And the G is the imaginary part of the forcing f hat and the real part of the forcing f hat. So what I've done here is I've rewritten this as a first order ODE equations in terms of as a system of first order equations for the real and imaginary parts of the field, of the perturbation field, which is complex. But now I've broken it apart to its real imaginary parts, and it takes this form here. So this is a really nice representation of what happens for the linearized operator. And now it's all written in terms of real components. Okay? So the main thing to talk about, you have the linearized operator. What we know is that G, which is forcing it, G better be orthogonal to the adjoint null space. So I better start learning about the null space of this operator's L. And notice the operator L has all these L plus and L minuses floating around, so I really need to start learning structure around that null space of that operator. So first, a couple things to highlight about L plus and L minus. L minus itself, its null space is this non-trivial solution, which is the hypersolic secant. So I'm going to have to take that into account. So that's going to impose some kind of constraint, right, that I have to be orthogonal to this to get a solution. The L plus operator, notice it has a null space spanned by a such tangent. It also has a positive eigenvalue, which is such squared, which is negative 3 such squared. So this here has an eigenvalue at minus 3. This here has an eigenvalue at 0. This just has an eigenvalue at 0. There's also something else interesting I'm going to show you because it's going to show up everywhere we go. You're going to get L plus acting on L minus and L minus acting on L plus, and they both have null spaces. In fact, this is what's called the generalized null space, which is L plus acting on this vector is 2 such. Then if I acted on L minus on this, L minus acting on such is a null space. So you have L minus L plus of this is 0, and L plus L minus of C such C is 0. So this is going to contribute to our null space. And in fact, that operator that we have has a null space spanned by 4 vectors. There are 4 0 eigenvalues which span that null space. That means the right-hand side is going to have to be orthogonal to the adjoint null space, which is going to be spanned by 4 0 eigenvectors. In fact, here, let me just draw this. So L minus itself, here's its spectrum. It's a continuous spectrum to -1. We haven't really talked much about continuous spectrums, nor will we much in this class. There's a 0 eigenvalue here. That's the one I care about because that's the null space. Then you have L plus. Here's the continuous spectrum. Again, a null space and a single vector out here. And then when I look at this, the operator L, which is the operator, remember, L is this vector here. So it has the L plus L minus in it. So I want to start considering what are the eigenvalues of this. So it's not L minus and L plus by itself, but it's this combination. Then L and L in its adjoint both have spectrum that looks like this. And you have a continuous spectrum to 1, continuous spectrum from -1 down. But the most important thing is here, there are 4 0 eigenvalues there. And in fact, with 4 eigenvectors that we have to consider there, which means that we're going to have to take this right-hand side, and it's going to have to be orthogonal to those 4 eigenvectors that sit at the 0 there. Okay? So there's a lot of details I'm skipping here. Mostly I want to highlight what goes on here, and there's a lot of papers that have been written about this specific example, and a lot of details that you can find in the notes. I make reference to some of the key references that have really done a very rigorous job in characterizing this. Mostly what I want to highlight is we've expanded around the solution. We've now have this perturbation problem for the linearized operator, which has those 4 zero eigenvalues, which are going to require me to enforce the solvability conditions there. And in fact, here are those null space eigenvectors for the 4 zero modes that I have there. This vector, this vector, this vector, and this vector. So the perturbations are going to have to be orthogonal to these. Okay? And when you impose that, here's what you get. You take the inner product, you impose those solvability, and so there you go. Make it orthogonal to the null space. So such times the imaginary part of f hat has to be 0. In other words, it has to be orthogonal to the adjoint null space. Same thing with this, same thing with this, same thing with this. 4 conditions. As you would expect, if there's 4 zero modes, you're going to have to enforce 4 Fredholm alternative theorem type structures, right? Which is has to be orthogonal to the adjoint null space, and the adjoint null space has 4 eigenvectors, and this is the implications. 4 constraints. Now this is interesting. How many free parameters did I have? Remember, that soliton solution was had 4 free parameters, and look at this, I get 4 constraints. And so this is going to allow me to go and actually, when I plug in some generic perturbation f, here then is the slow evolution of those 4 parameters. And there's a lot of algebra that I'm skipping and showing you this. But when you impose that, it's telling you the evolution, the slow evolution of those parameters that characterize the soliton have to evolve according to these equations here in order for you to be orthogonal to the adjoint null space. And so this gives you specifically the slow evolution equations of those parameters, which is fantastic, right? So now you've got this correction, you have parametrization of the soliton, and you actually have the slow evolution of those parameters under perturbation, which tell you everything you need to know about that system. Okay? As a specific example, you could have said, well, what happens if in that nonlinear Schrodinger equation I have a little bit of attenuation, a little bit of a loss? Then your perturbation looks like this, minus I gamma u, and gamma here is just the linear attenuation. And if you plug that in to the slow evolution equations here, you take that very specific form of perturbation, plug it into these evolution equations, here's what you get. Attenuation just says that the amplitude is slowly decaying. d eta d tau, so on some slow scale tau, it's minus 2 gamma n. So you can write down the solution to this as just it's an exponential decay on some scale, on a tau time scale. In other words, this exactly makes sense. If you have damping, the amplitude is just going to die. And notice what it does to the others. It doesn't shift the phase or frequency or position. It only affects the amplitude. So this is the kind of insight you can get in sort of this description of spatial temporal systems where you perturb around a governing equation and you assume that your leading order solution has slow dependencies on the parameters, and you just essentially do what we've talked about this whole course through, which is make sure that when you get your linearized equations with a right-hand side term, make sure that right-hand side term satisfies the solvability condition. And in this case, when it satisfies the solvability conditions, you get out some very nice and interpretable evolution equations for how the leading order solution is changing and what its stability properties are like. So this is one way to handle perturbations. In the next lecture, we're going to talk about introducing slow space and slow time scales, and we're going to develop envelope or order parameter descriptions of what happens at the bifurcation points.